this last clip of the series, I am going to consider what happens if the filament is not really infinitely long, but truncated at some height a from the galactic plane. That is, the source of gravitation that gives the flat rotation curves is elongated or prolate, but not infinite. To deal with a finite cylinder, we cannot use Gauss's theorem so easily, as flux escapes over the caps. Therefore, one can resort to direct integration over the line perpendicular to the galactic plane, and instead of extending the integral to infinity, truncate it at a. The velocity in such a field now starts falling again as shown in this equation. This becomes appreciable when the distance r to the center starts becoming comparable to a. The Spark database does not really contain galaxies with this break of the flat rotation curve. At most, there are soft decreases that could be compatible with a spherical component whose associated velocity dies out. My students in Madrid are studying this seriously and trying to produce best fits. Nevertheless, the decrease has been claimed for the Andromeda galaxy, as can be seen here. The data has large uncertainty bars, but it would suggest that the velocity indeed starts decreasing. If the decrease is about a part in 20, as large as the uncertainty bar, at the first falling points, the height of the cylinder is calculated from that formula to be just a bit larger than 1.5 times the distance at which v of r starts falling. Let's call it r sub break. So, if for Andromeda this break of the velocity curve happens at 0.1 megaparsec, the equivalent cylinder of dark matter that will be causing this velocity would roughly extend 0.16 megaparsec above and below the galactic center. Let me turn to dark matter simulations. Generally speaking, because the halos computed in these simulations arise from the mergers of more such halos, they are often prolate like a rugby ball. The right plot shows that for galaxies approximately our size, the dark matter halos are 60% of the time prolate and only 15% of the time oblate. This is in stark contrast with other astrophysical bodies, such as the Earth or other planets, stars, neutron stars, and so forth, that are oblate due to the centrifugal force pushing outwards of the rotation axis against gravity. Here we have an extraction from the illustrious simulation. The S parameter, a measure of the prolateness that is closer to 1 the more elongated an ellipsoid is shown to be significant. The graph on the right shows that even the mass dependence can be extracted, checking out how this S parameter varies from light to heavy halos. And this last graph, with the distribution of halos among prolate or oblate in the Millennium simulation, shows a definite preference for prolate halos. There is no shortage of them. To conclude the series of videos, I have exposed an analytical limit in which the rotation curves of galaxies are flat, with velocity independent of distance. This limit is just having a source of gravity that gives space cylindrical symmetry. It is really an obvious way of obtaining this zeroth order physics, and I do not know why it isn't in every textbook. It's as obvious as Columbus' egg. Now, if you want to adopt the currently conservative point of view that dark matter simulations resemble reality, they are providing us with a large number of prolate halos. If spiral galaxies form in the belt of these halos, then the stability of the rotation with a flat velocity is only approximate. At sufficient distance from the galaxy center, there should be a break reflecting the size of the largest axis of the halo ellipsoid. I hope you enjoyed the story, and thank you for your patience.